Yeah, started the recording. Yeah, go ahead.
Am I audible?
Yeah, you are audible. Am I? Hello. Do you hear me?
Yeah, I can hear you. Okay, it's fine.
Yes.
Okay.
Actually. Yeah. Can start then.
Sure.
No, let me see. Yeah. So okay. Our problem is tiling a rectangle with fewest squares. So we are given a rectangle of size n cross m, and we have to find the minimum number of integer-sided squares that tile the rectangle. So these are. Let me try. It's what is it? 2 cross 3 rectangle, right? So we have two squares of size 1 cross 1, and the remaining space is tiled with one square of 2 cross 2. So total of 3 such squares, minimum number. So here again, this is the arrangement for 5 cross 8. Right.
Okay. So 5 is the width.
Yeah.
And 8 is the length.
Yeah.
So in that you can only place a bigger rectangle, a bigger square of 5,
Yeah.
then a square of 3, size 3, and then 2, and then 2 rectangles of size 1. Okay.
Yeah. And next, this is yeah, this is except,
Yeah,
I mean,
example 3 was interesting. Huh?
yeah.
So what if, like, in example 3 we have 11 row and 13 column, right?
Mm-hmm.
Then if we make the square of like size 11,
Mm-hmm.
then how many square we need? Maybe it's more, right? Because now we have only 2 column left, right?
Yeah.
Yeah.
11, 13 subtract 11 become 2, and yeah.
So then you can form two squares of each. So then we can form 5.
And one more 1 cross 1.
2 more, right? The last
Two
one
one.
is like 2 column, 1 row. So we have to make it become 2.
So how much that comes to? 1 and 5, 6.
This is your 11 cross square you fit, right? Now this is 2 of that is left. So this is what this height is 11, right?
Mm-hmm.
So 5 such squares will fit here, and at last 1 cross 1 square will fit. So this will occupy 10, and this will be 1 plus.
Is it 1 or 2? 5.
This will be last one will be. Yeah, go ahead.
The last one is we have to break it into square, right?
Right.
Yeah, 2 squares here, right? Something.
So in all we have 1 here, 5 of those 2 by 2, which will be 6, and this 2 of 1 by 1, 8. Right? So we are having additional 2 more than what the answer says. And the answer says that you can have minimum 6.
Yeah.
Yeah.
So it will not work. Right.
But like based on that, then the size of the square could be different, right? And then it's difficult to see in example 3. We see a square 1 in the middle.
The 11 arrangement was also answer was also 6 only, right? 11 by 11 and 4 3s and 2 1s.
Okay, let's see that. How come?
Our n is roll, I mean width, right? And 13 is your 11 cross 13 it is, right? 13 is what? Height, right? Is it? and 11 is your.
Yeah. No,
So
13 is, no, 11 is a row, 13 is a column.
okay.
So
Yeah,
you do
whatever the way it
reverse.
is.
Yeah.
Either way it should work. Right?
Yeah.
Yeah.
So if you have, say, like a square or rectangle size of 2 by 11, so in that case, we can make squares of 2 by 2, right? So they will account for 5 of such squares, which will consume about 11, sorry,
Hmm.
10 of the space, right? 10 by 2.
Yeah, 10 by 2.
And then we are left with 1 by
3.
2, 1 by 2 space, which will actually make us two of those, right? So 2 squares of 1 by 1. So therefore, we'll have 5 squares of 2 by 2 and 2 squares of 1 by 1, isn't it? Or you have something else to say, Uday?
No, I thought it was 3 fours. Okay, sorry. Yeah.
Oh no, not
Twos
3,
are
4. Yeah,
yeah.
maybe we can make it 3. Yeah, but we might reduce maybe by 1. Oh no, but because that's odd length, you can't actually, right?
Yeah.
Hmm. And I think this is the only special case, right? If we even take care of this case, most of the normal approaches work, right? In this case.
Yeah, this is the only unique one. And this for the last.
So in example 3, what is the size of square number 4? Is that
Square number 4, this one you are saying.
yeah? What the size?
It's 4 by
Size,
4. No?
you are 4 by 4. Yeah.
Is that 4? Oh,
Yeah, all
Yeah,
of them are that.
that's,
4 plus 4, 8 plus 5, 13.
oh, okay, yeah. Yeah, yeah, okay.
One way is like, I mean, if you are using horizontal wise, so a K width slab you are fitting here, right? So recursive call you will do for whatever length. If this is I, it will be I minus K, the number of ways you are filling this, plus F of K and J, right? This is the way when you are using the K width slab. I mean, vertical, this wise, what you say, vertical one.
Correct.
This one call. And the other call, if you use it, what you say, horizontal wise, then it will be just F of I J minus K plus F of I will be as it is, and this will be K. Right.
Yeah, yeah.
These are the two for horizontal and vertical. But this one is like not coming up in this.
Yeah. Yeah, so that's the only special case. Yeah, but without, if we just handle this special case separately, so and the formula what Shashank has actually, he has just displayed here, right, for the horizontal and vertical. So if we take care of this one, then we are good. I think that also is a fair uh, approach, right?
Yeah.
And it passes the lead code. Yeah, but they say it's a cheat, right?
Yeah, people use it N13 and 11 and then
Right.
pass it.
Yeah. So that works. But worst case, actually, I think this should be also okay in interview. At least if you are able to break it down, okay, the way you think, you know.
Can you explain again, Shashank? So
So
from
if
I
we,
to K.
I is the length, right? This
Okay.
this. So if you use a slab of tiles of length K, then remaining length to be covered is what? I minus K. So
Okay.
you already got the number of, I mean, there is only one way to cover this, right? Because K length slab you have and you fixed it. So just you have to find how many number of ways you can use to fill the other slab, I minus K, and this is your constant J. And the other way around is if you just invert this slab like this way. So K you have already covered. So remaining in the horizontal direction, J minus K is left. So what is the number of ways to fill this?
Well, K is not constant actually, K will be,
Between.
yeah, you will have to actually keep on moving the K to find the most optimum value, right? You'll have to find the minimum value. Okay.
K will actually should run
Yeah.
from I.
So K will actually range from 1 to maybe half of J in some case. When it is, I think it's a horizontal movement. If it's a vertical movement, it should be then
J-
1 to I by
J-
2, right?
J-
So you'll have to recursively go, okay, with all these different what you say, the divisions, right, for the K.
Hmm.
Yeah. So
But
it's not a single value.
the way I see that is doing this way still break the problem in a smaller,
Re-
rectangle. But
Right.
Yes.
then finally we still need to solve somehow. Let's say, if our smaller rectangle is like in example 3, then how this way gonna solve it?
Okay.
This
Yeah,
will
that
That
can be
small.
solved also. Yeah. But let's actually just focus on this one first, then we'll come there, Leon. Okay.
So this one does not. Are you saying this one will do? We also handle the example 3 we will discuss later, or
No, it won't handle example 3, but at least it will handle about 80% of the cases, maybe
okay.
90% of the cases, 99 maybe. This is the only one case, right?
Yeah. Okay.
Yeah. And it's on the size also, the constant of n and m is also not more, it's only 13.
And one more question: why you are running K till I by 2 when horizontally we can't go more than that?
That's a mirror.
No, you have to, yeah, it's a mirror, yeah. Because then everything will be repeating after that, right? So you have to optimize that.
Yeah, got it.
Yeah.
So for the horizontal you do I by 2, and for vertical J by 2.
Right. It's like what we have n and m. So we just n by 2 and m by 2, then we are good. And if we handle this corner case, then we are good. So at least for the first approach, it works. Okay, then we'll have to look for what Leon was saying for this example 3.
For
So just like greedy doesn't work, right? Greedy, like we do the square. Yeah, like we see that we always go with the biggest square.
I don't know whether greedy will work, but at least you might need DP at least, because if you are going through at least memoization, the top-down approach, you know. I'm not sure. I never tried with commenting the memoization part, but it still works. Hmm. Yeah,
the
sorry, go
greedy
ahead.
with 11 cross 11 square, right? Because it was giving larger number of squares.
Yeah, if it's perfect square, then we have the answer.
Hmm.
Okay, so how would we think? How would we approach the
Okay, so
classification?
let me display the first approach and then we can discuss about the second one,
Yeah.
the third one. Okay. So because that will take some more time, right? At least finish the very basic thing first.
Okay.
I think because of third only it becomes difficult, right? Hard category.
Right. That is correct. So this is the way I was talking, if you handle this base case, okay, right now I'm not handling it, of 11 by 3, okay, and then you use a normal recursion. So we have this n and m, I'm just passing from this input parameter and then a dp of memo. So these are the base cases, like if n is less than 1 and n and m are greater than 13, so we just return the max value. If both of them are same, then it leaves perfect square, so it is 1. This is the memoization part. And so this is what I was talking about and what Shashank said, right? So you start from a value like I, go to n by 2, wherein n is maybe row or column, whatever it is. And then you actually run this I, okay? It is like 1 to n by 2. And then you keep this other part, maybe this is the vertical one constant in both cases. And then you are actually dividing the sub problem into I and n minus I, because n is the maximum, right?
Yeah.
So you'll have to keep dividing this, and then you keep on finding the minimum and just store the minimum with this variable. So the same thing you do for the vertical side. So what he was showing exactly the same thing. Just run from I1 to M by 2. And then when you are done, you just find what is the minimum of both of them and then store it in your memo.
Yeah.
Yeah. So this is a very simple approach, and the way we actually have been dealing with DP, right? So this completely works except for this corner case.
So you take minimum in horizontal and in minimum in vertical, and after clubbing them again, you take the minimum.
Right, because you have to take minimum both of them, right? Because whenever he is actually dividing in these two, because he will go recursively again, right? So even if you find something in the horizontal, you still come to the vertical also, right? So the recursive call will keep on finding the most minimum value, and then you return that value. Yeah, you have 4 recursive calls, and then you are subdividing the problem across the vertical and horizontal side. Yeah. So that is one way. Now let's discuss about the whole approach what Leon was talking about.
Yeah, Leon.
One quick question. Why are we checking it for n by 2 and m by 2 now?
Because after that it will be repeating. You see, n by 2 is the mid of your that whatever what is saying this board it is, right?
Yeah, because that will be your half part. So even if you go the other side, you are going to get the still same values, So you optimize over there and just prune it. So now this way, yeah, Shashank, what?
I mean, I was going through that this one.
Yeah,
Third
that's perfect. Yeah, that's the one I was also going to refer. Yeah.
Okay. This is like what you did, ix minus I.
Correct. Let's go to the main one. Yeah, this guy. These 5 partitions, right?
Yeah, 5.
Correct. Yeah. So if you go through this, that makes more sense now, right?
Yeah.
Can you explain what you mean make more sense?
Okay, so now this is they have divided the whole thing into 5 rectangles. Okay, out of the 5 rectangle, the P5 is a square, and they maintain that square always. So you can expand the square starting from one dimension all the way to the max, maybe whatever, all the way to the minimum of y and x. Okay, so then when you are expanding, all your partitions P1, P2, P3, P4, they are also going to get they will align with that. Okay, so in case if we actually move this P5 all the way, okay, so in some cases your P3, P4 may go away, correct, in the extreme cases. So if you imagine that way, and that is the thing what we have to do. So we have to keep on expanding this from one dimension to all the way to the maximum, and then look for all these P1, P2, P4, and P3. So these rectangles, actually we need to find the minimum of them.
But
How
so
much square
where
you can
we
fill in.
start the P5? I mean, where would be the starting point for the top left corner of P5?
P5 actually they start from the inner side, maybe like 1, 1. Yeah, the innermost part of it, and they go all the way to the minimum of whatever is x and y. So in this case, it looks like y is the minimum one. So you can have a square of y by y. So I think P5 in the way it is shown will cover all the portions of P3 and P1, correct? And he will only P2 will remain in that case, correct? So rest all the rectangles will go away. So that will be the extreme case.
What about P4?
Okay, let's, even if we draw it, so I think P4 should go away, right? So if I expand this like this, okay, so will this not P5 be like this? Sorry. And then you are left with P2 here, because this dimension also is going up, right? This, right? So he's going to push this P4. So you're only left with P2. So because it is aligned this side, right? So if it was aligned this way, you could have actually suppressed, I think, P2, and then only P1 would have been there, right? Something like that. Just for an imagination sake. So that is the way actually you'll have to visualize.
I would like, in that case, we see only P2, right? The way you draw it, only P2. When would we see like P4 only on the right side?
Y and then X.
Yeah,
Right.
actually, our intent is not actually that, but that was the maximum case, right? So what we'll have to start from the most smallest one, rectangle of P5, sorry, the square of P5. And then actually, when this is so small, then we actually have to find what this guy will be. So in this guy will be like this. So this guy will be like this. So something like that, right? And then we find our minimum values for P2, P1, P3, P4, and then it keeps on expanding. So this also actually won't go to the very extreme. It might end up within X by 2 or whatever the value is from year to year divided by 2, right? So that will be the optimum value.
So in the code, P5 can start at the 0, 0 top left corner and keep growing and moving.
There is no starting coordinate, right? So they're just taking the dimensions. So it's 1 by 1. If you take 0 by 0, I don't know, because if then the other rectangles won't fit, right?
And
Because
it will go out
it's odd.
can't expand on top if you start from 0.
Yeah, don't you need to know like the position of P5 to know like the size of P4 or P3? You don't need to know the position.
Well, I don't think so, because then they all fall in that place, right? Because when you actually, we play with this K and this I, okay, so that is what is important for us. So we actually expand K and I. So I will actually go from here all the way to here, okay. Maybe we just keep some of these, whatever that center square size will be. So I can go from 1 all the way to here, okay. Same thing, K can also go from this value all the way till here. So we are actually covering all the spaces that way,
Yeah. So that IK determine where the P5 position be.
Right, it will push the P5 that way, I and K. So then it will cover most of the places, yeah.
Yeah, Santosh, one question. Like, how do we the other configuration can be P4 can be down, like P4 can be in the same uh, length, like same bottom as P5. Basically P2 is shrunk down and P4 is to the right. So how do we, consider that also?
So if we take P4 to the extreme right, you mean to say, right?
I mean, right now P4 is on the top of P5, right?
Mm-hmm.
The case where P4 and P5 are the base is the same. They are at the same level.
Okay,
Like,
you are saying that P2 will go away complete, right?
no, P2 will be height same as P1.
P2 cannot be the height of P1, and P2 cannot match, right? Because
It has to be square for
this is the right, so maximum the way actually they are showing. So it
Yeah,
can
I mean,
go
what I'm saying is the
Mhm.
left edge of P4 will align with the right edge of P5.
Left edge of P4 with align with right edge of P5.
Right edge of P5, and bottom edge of P4 will align with bottom edge of P5.
Uh, well, there are different ways to do it, but I think here in this case they are maintaining this, right? P5's left edge, okay, and P4's left edge. So that is what they are doing. But what you say is right. There will be different configurations, and there are many people solving it in different ways. Yeah, but this is one way actually we came across, because even if you see at the example 3, it's not exactly the way it is represented here, right?
Yeah. Yeah.
Some of them say, like, you take this P5 in center, and you start with the square from this side and start with the square from this side, and then you bring up both the squares together, and then you make this in between that, and then you have this other space. So that is also a good example. But
Yeah.
I was following this, I could understand it, and therefore I just thought of, yeah. So
Yeah. This I was just thinking out loud how it covers. Does it cover
yeah,
all
it
the
should.
scenarios? That what I was
Yeah.
thinking about. Yeah.
What is the minimum size of P5? Does it can be 0 or have to be at least 1?
It has to be 1 at least. Minimum should
And
be 1.
if it at least 1, then the left of P4 would never on this same as the right of P2. I mean the right of P5, right? The left of P4 never be the same as the right of P5 because the size at least 1.
So even if you imagine this itself as a 1 by 1 matrix, 1 by 1 square of P5, so will that not work?
No, someone would say if it the left of P4 might be the same
Okay.
as the right of P5, right?
Yeah. So
It
Raj
only
had a
happens
different, yeah, that is correct. But there are different ways to solve it, So this is just one way of solving it. So what he's saying, there is one approach, and people use that also. But then you have all those complex ways of doing it. So if someone understands that, that is good. This is also not so easy to understand, but I think Shashank also understood it, right? So when I was
Yeah,
going through, I was able to follow it. Yeah. But Raj, we
Yeah.
can
What?
discuss your approach also if you have that handy.
No. I don't have it. Like what I was trying to understand is like if you see the example 3,
Mm-hmm.
it in there the answer is the right edge is aligned with that small one
Correct,
square.
correct. Yeah.
So how this we are expanding it, how the one we are going through, how it will cover that. That's what my question
Yeah.
was.
So see, anyway, in this case also, if you look at it, if you're, oh yeah, can you please go to that example, Shashank? Yeah, sorry. Yeah. So if even if you say this is still a square, okay, 1 by 1 square, and you still have these 4 rectangles. This is one, okay. This is a second rectangle. This is third rectangle, and this is the fourth rectangle actually. There one rectangle. Now he has shown like I can divide this into 4 by 4, because similarly we'll have to do for this 7 also, right? We'll have to divide with the same algorithm what we were discussing earlier, right? So we actually divide horizontal and vertical and then find the minimum here. Same thing we do this rectangle, this one. So everyone is trying to divide it into 4 rectangles, right? As long as you are able to divide it into 4 rectangles, and when you have one single rectangle, you follow the normal way of actually getting the minimum, and then come back, and when you have all the minimum of each and every rectangle, then you actually go with this approach of 1 by 1 and keep on expanding it all the way to the extreme case. So then you'll get your answer.
So you saying recursively solve it for the 4, right? One you break it to 4 rectangle, you recursively solve it, right?
Yeah. We have to recursively solve for all the 4s. Yeah, absolutely.
So in that case, in the top left rectangle, we have 4 right there, right?
Mm-hmm.
If we break it down into like recursion and we solve it, where would be the square 1 in that rectangle?
You mean to say in the 4, 4?
P5, yeah. Where would be P5 in that?
Okay, so now in this case, you will have a base case, right? Because you are able to form a 2 squares immediately with 4 by 4. Therefore, they are representing it. And so when you are able to form in the base case, when you know you can form a square, you will just get out from there, right? You don't have to come to this case at all.
Yeah, but this one is not the square, right? This one, this is one of the rectangle I'm going to recursively.
You mean to say this 4 by 4, right?
Yeah, that.
Yeah. So when you are a year, okay, so you follow the way Shashank was saying, right? The first one. Okay, you actually divide it into the vertical side, okay, and then you keep on using this, the minimum and maximum. So when you come to the center, you know that you are able to form two squares. So your answer will be the most minimum 2 for this rectangle. You cannot go lesser than that, right? So that will be the minimum. So you will have an exit from that base case, and then you won't come, and you won't come for this case at all, like this one. So you
Yes,
come to
so,
this case only when this is the most minimum one, right? So but
so
you, if
you
you
have
are
to
already
try,
have. Mhm.
you have to try to solve using Shawshank approach first. If it doesn't work, and you use this P5 approach.
Yeah. So this is the scenario 3, what he is talking in that case also. So the first two, what I was discussing, were the scenarios 1 and 2, and then this will be the third scenario. So if you are not able to come, you are not able to get the minimum in scenario 1 and scenario 2, then you come to scenario 3. Okay.
Mm.
Yeah. Okay. Yeah, Shashank. So you, yeah. So you want to explain that problem, right? Yeah.
Shall we go through code? I think that will be.
Sure. Yeah, no problem.
So this is like base. I mean, if I and j both are equal, like if it is a square, then only one way is there, right? One way to fit. And if x is 1, you return y, and if y is 1, then you return x.
Yeah. So if it is 1, then whatever the value of x or y will be, that will be the number of squares, right? Yeah.
Right. Yeah.
Because y. And now result, first of all, we are multiplying x and y. I mean, this is the maximum possible, which will consist of, if everything is a single square.
Right.
Or you can take any max value also, but it's better to, because the worst answer will be this only, x cross y. So first scenario is that what you said, like two DFS calls they are making on I and x minus I. This is for these two cases are for the normal cases, right?
Right. The first one, too. Yeah.
Here becomes the third one. What he's doing is taking minimum of x and y and starting from 1 and taking every point as center every time. I mean, whatever the minimum of that is, right?
Yeah.
And for that, from 1 to the whichever is minimum, is subtracting that center part and getting the complement. What do you say? Remaining part for it. And k is also running the same way.
Yeah.
And then partition 1 is 1 plus center square size k, and the other will be x minus I minus this. Because if you subtract here, it will, that center size will add to the kth, what do you say, on the y side. It's like expanding in that direction, right?
Yeah. So these are the P1, P2, P3, P4. These are the rectangles.
Rectangles.
Yeah. And then if you actually try to map or look back in that diagram, so it will make more sense, because now what k is, yeah, if you look for the P1, yeah. So we have k over here, right?
Yeah.
This is the k. And then if you look for its width, okay, so this is the width maybe, and if the length will be x minus whatever that value, right? X minus I, right?
I minus size, center size.
I minus center size is x, okay. So then that will be our, so he is trying to calculate this rectangle. So the same way he'll follow for the others also, okay.
And a center is only taking from 1 to the minimum of x and y, because it will go only, because if we take maximum, then it will hit out of the square. That's why his minimum is taking.
Yeah, right.
But it's very highly manufactured, right, solution. Like if you don't remember that, then it will.
Yeah, but some of the solutions, if you know it, you know it. It's like that, you know. You cannot come to this solution at all, right, in an interview. So you have to know the solution, you know. And then when you know the solution, you explain it, then you're done. So that is what everyone is going to expect, because these are the classic cases, you know.
Exactly, yeah.
Yeah. So there is no theorem. You cannot invent some of the things, right? But you need to know them.
In that case.
Yeah.
And it will always be 5 squares only.
Yeah, there will be five rectangles actually. So the last one is a square.
This is the center one, yeah. Okay.
Yeah, that is center. Yeah.
So it can never be more than 5, right?
No.
Okay.
So if it is more than 5, then it is better to go by the previous scenarios, right? 1 and 2.
1 and 2.
So you will surely find something better there. So if you are not finding any better in scenario 1 and scenario 2, then only you come in the scenario 3. So there might be some theorems and proofs on this. Yeah.
Would it improve the performance if we use the cache as a way to samples?
Yeah, he is also using the cache. If you see the LRU cache.
Oh, this is
inbuilt cache, yeah.
Is in memorization. Python has, yeah.
So yeah, Python. Okay. But how would you calculate the runtime complexity for this?
Okay.
These two equations, mainly these two equations are covering your runtime count. No, it's not like that.
So it is exponential, but not exponential, because if you are doing caching, in that case, it will be at least n cube, right? Or maybe, because if you look at the scenario 3, right? No. So therefore, I think it is at least n cube, or maybe more than that. I don't know. I'm just thinking loud. Anyone can actually pitch in here.
And you have recursion calls also for every.
Yeah. Therefore, I was a bit skeptical on it. Yeah. I don't think anyone is even discussing about the runtime. Right.
In official solution, nobody hasn't mentioned anything regarding time.
Do they have an official solution? They don't have.
Each possible combination of is calculated once, then for loop for varying size of this times with.
Okay, so the overall time complexity comes to n square m. Okay, so almost n cube, right? Okay.
How did they calculate possible combinations?
So he's actually looking for the 3 loops, right?
Yeah.
Yeah. Then what about the scenario 1, scenario 2?
So it will be n square. If it's only scenario 1 and scenario 2, if you don't find, go for the other, it will be n square, right?
Otherwise, minimum of these two.
Yeah.
This is a hard problem, and it's beautiful too, right? It's
Yeah.
Yeah.
It's very beautiful. Yeah.
The last one really makes it beautiful.
Yeah.
This.
Yeah. I think that's the max. I think.
Yeah.
Yeah. Raj, do you want to go through what you were discussing? Anything?
No. I was just trying to understand. I joined a little bit late, so that part I was trying to understand. Yeah.
Okay. Yeah, but there are different ways actually people are trying to address this issue. This especially the example 3, and it's very interesting. It becomes very interesting if you keep on following many of them. But most of the time, what you do is you start with one thing and you want to end it. So when you understand that, you don't want to go to the next one. But sometimes it happens. Some other person actually has followed the other example, and it's always good to share, and we can discuss that also, right? So yeah.
Yeah, I mean, I saw a video on the skyline, but I didn't like. That's what I just saw it. But yeah, this I think this one is better, easier to understand.
Skyline was there. I didn't get like what they were explaining.
There is some video on this also.
Yeah, one guy has made some skyline video. He was saying that, let's say, these things. I mean, this is filled. These are. So first he was telling you have to fill these grudges. I mean, these grudges, the number of squares required. Now you'll have an even shape, something like this, right? This one. This you can calculate very easily, right? Because that's a proper shape you are getting. But filling these grudges, these will be what do you say? I couldn't follow much. He was saying that we look only at whatever till this point you'll have some coordinates. You will have some coordinates here. Again, you'll have some coordinates at this point and this point. So this you are getting, right? Also you are getting. So if you can calculate the number of ways of this, filling this, and then this is straightforward. So just something like that. Sum them these three.
Okay. Please share that video. Let me also go through it. If something interesting, then we can discuss sometime later.
Yeah, sure.
I was actually thinking maybe we could do it. I mean, I will still implementing it, but I was thinking in a different way. So, so the rectangle area has a area of m into n, right?
Yeah.
Yeah. So I was thinking. So you need to express m into n as sum of squares.
Oh, yeah. So,
So you need minimum integers to represent the sum. I was taking it like that.
but everything is not a square here. Rectangles are also there.
But I mean, I don't know. I was trying to say 1 minute. Can you go to the description?
Yeah,
Yeah. So if you see this one, you need to fill with squares only, right? So Can you go to the examples? I mean, some slide down. Yeah. This one. Take this one itself. So you have 5 into 8, 40. Now you need to represent 40 as sum of squares. Uh, so that would be 25 plus 9 plus 4 plus 1 plus 1.
yeah.
So did you get what I was trying to say?
Yeah. So minimum number of squares you have to find so that when you add them, its area should be equal to the entire area of rectangle, right? X into Y should be equal to
So I think you are trying to say a square of 1 by 1 unit, right?
no any square, right? Like
Yeah.
1 into 2 into 2 and 3 into 3 and plus 5 into 5, right? You can minimize, like if we have to say,
You need to express x and y as sum of squares, and you need minimum number of squares to represent this number. I'm thinking that the sum is that.
Yeah, but will that handle the scenario 3?
yeah, that is what I'm.
Can you go down?
Yeah, because this one will work with the first and second scenario. So yeah, this guy actually.
I'm not sure if 6 is the least value for squares as well. I need to check, but I was thinking in that direction.
Yeah,
But
that is good actually. Yeah.
These are all squares, right? I mean, if we can represent the sum of m into n as may or may not be the same direction, but haven't got any failing case. I mean, contradicting case or something, which may or may not be possible then.
Okay. So did you
No.
implement it, or you are just thinking?
No, I was actually thinking in a direction and I was implementing it. I haven't completed it.
Okay.
Actually, what you are thinking, there is a problem also. 279 minimum number of perfect squares which you have to get. I'll show you. I mean, that's also
Well,
DP
okay, okay, yeah, we'll go there. Yeah, but if you look at the way, Uday, the only thing about this problem is, okay,
Yeah.
yeah, I just want to, now if you go back to the description, yeah, so, okay, yeah, no problem. If you go in there, it's fine. So if you look at the example 1 and example 2, he's always dividing either in the vertical side way or in the horizontal way. So he keeps on dividing in the vertical way first, and then whenever he finds all the squares, so whatever is remaining rectangle which he cannot break it, then he goes into the horizontal side. So based on the dimensions, and that will work. But when you look at the example 3, it is not that way. He's starting from the middle. He's taking a square from middle and then he's expanding it, right? So there actually you cannot form rectangles in a horizontal and vertical way, right? So therefore, this actually, doesn't actually, this approach, maybe it's not very. See, if you look at example 1, he's actually breaking down the first square, and then he's going for 1 1 in the vertical way, right? So similarly, if you go for example 2, he's doing. Can you scroll down? Yeah. So the first one is actually when you finish with 5, right? So then you come to this vertical one, right? So this will be, you finish this one, then you come to this rectangle, and then you break it down into vertical like this. Then when you are left with another rectangle, you know that it is this dimension is the maximum. So you actually break down on the horizontal side like this. And now if you look, this dimension is maximum, and then you break down on vertical side. So therefore, the way the scenario 1 and 2 actually work for this one, but when you come from, when you start breaking down the problem from inner square, that will be slightly different way of thinking, right?
Yeah.
So, but then the way you are saying, yeah, if you are just um, trying to find the number of squares, yeah, maybe it might work.
No,
You're
but
breaking down into a square of 1 by 1. I
here
think
I
there
think
is some people actually describing that approach also in the discussions. Yeah, sorry, Sharan, go ahead.
no, I'm saying, but here you're breaking first into rectangle and then into smaller squares, right? What you are saying, that makes sense. It won't work in this case.
No, but
Directly, we are
he,
not breaking 1 cross 1 square, right? You first break it into rectangle and then you find if it's possible to break into something
yeah,
like this, right?
correct. But he's going the other way. What he's trying to do is he's trying to break the whole of the problem space into a square of 1 by 1, and then he's trying to find what is the minimum number of squares he can get.
Yeah.
So yeah, that might be one way. But I was just thinking how you'll have to take care of that condition also, right? The one which we start from the center. So
Center.
yeah, maybe there is way to do that also.
Yeah.
No problem. So if you have that solution, just please share.
Yeah. So shall we move to next or?
Hey, let's move. Yeah. Sorry about that. Actually, can you cancel this?
Yeah, sure. So next is like ambiguous coordinates. So here we have two-dimensional coordinates like this and this. Then we removed all the commas, decimal spaces, and ended up with the string. We have to return a list of strings representing all the possibilities for our original coordinate from what our original coordinates could have been. So it's like, I mean, 1 2 3 is there. First they are breaking into 1, then 2 3, then 2 3 is again splitted into 1 2.3. So whenever we make a break, make sure that at least one element should be there in one that, right?
Yeah.
Yeah. So same way for this. And yeah, your constraints are like this thing 4 to 12 and the other elements in the yeah.
So actually, in this, the thing is, if we have a 0,
Yeah.
that is the most critical thing, right?
Yeah. Starting here because it will.
Yeah. So if you have a 0 initial, like in example 3, right? So if you have a 0 at the very beginning, so you can still make 0 and 1 2 3, the first one split actually, but you cannot make 0 1 and 2 3, right?
0 1 and 2 3. Okay.
You cannot split that way, but you can still have a split like the one which is showing on this one, right? This one. So you can still make it 0.123. So that is
Yeah.
still valid. And this one also. Okay, but you cannot have 0, 1 and 23 because that doesn't make sense.
Yeah, it will.
Yeah. And then you can make still this one. Yeah.
Yeah.
And then secondly, in this example, right? So if your 0 is on the right side, so you can only go for 10 and 0. You cannot make 100 and 0.
Yeah.
Because actually 100 and 0 cannot, because that is going to be 1000 in that case, right? Yeah, that is true. So even you cannot make 1 and 2 zeros, right?
1 and 2 zeros, yes.
So that also not possible, because you can have a zero, single zero, okay, but not two zeros. So that is also not that. So those are the corner cases which are very important, correct?
Yeah, yeah.
Otherwise,
Otherwise,
if you have a zero,
otherwise it's like a normal recursion, MCM kind of like split at every point and then try all the possible ways, right?
yeah.
Like matrix 10 multiplication, not exactly, but something like that.
Well, this is, you are taking a string and you're trying to break it down, right? So whenever you break it down, if you just follow these rules, because you have to return the output here, correct? So I'm not sure whether matrician multiplication DP will work here. I'm also thinking loud. So it for me, it looks like you just break it down into different strings, right? And then you check by if the rules match, and if it matches, then you actually put into our answer result, right? Maybe a top-down recursion, that will be an easier way to think, right? Yeah. Yeah. Yep. You can have a different way of implementing, like bottom up also, but that comes more intuitive, right? About a top-down
Approach, yeah.
uh-huh.
So top down like that only, like I'm just splitting it at every point, right? And just checking all the possible conditions.
Well, will be, yeah.
Kind of, yeah.
Will it be a really top-down as thinking? Okay. Or maybe it's more of a string manipulation problem, right?
That, yeah.
Yeah.
Mostly part is that first digit should be 0 or not.
Yeah, but in that case, you'll have to break the string at all, what you say, like all lengths, right? From 1 to all the way to n minus 1 in this case. Because if we cannot break from 0, we cannot make one parameter empty. We always have to have a value in both the parameters, right? And that should be taken from both of the strings equally. Yeah. Okay. So I don't think so. Yeah, I'm sorry. I said it will be sort of a recursion, but yeah, it's more of a string manipulation problem. Yeah, and then the way you are saying, if we can do a DP way, yeah, maybe possible. I don't know.
Not
I didn't think about it.
somewhat normal recursion. I'll show you in the code. I think here you'll get it.
Okay.
So this is what I'm doing. I mean, at every I am splitting into left and right, right? I mean, till this will go into left and the remaining will go into the right. Passing into my helper function, right? Left combination, right combination. And now these are the two for loops. Like for every L in left, you make a combination with the right. And whenever you pass your left into helper, so this is the helper, like the all that condition. If the length of the word is 1 only, then you just return that word in the list. And if the first letter is 0, and make sure that the last letter should not be 0, then you return in this fashion, right? I mean, leave that 0 and then 0 point. I mean, kind of string manipulation plus leave that first character because it was 0, and remaining characters you take, concatenate with it and return it as a list. Right. And and again, if your last letter is 0, then we go through the 1 to the length of that word, and just till that character you split, put a point between them, and then again go from that character. It's like putting the point between the two. Like once you got the 12, 0 and 12, so 12 will again break into 1.2. That part will be done
Yeah.
here.
So on line 22, he says if the last letter is 0, he's not going inside this one.
Yeah.
Okay. So if it is 0, he will return empty. Okay. If it is
Yeah.
not 0, then he's going to actually place the decimals at each and every location. Okay. Yeah. Then it's splitting in different strings. Yeah, that makes sense. So that is one important thing, right? If you have a 0 at the rightmost side, okay, and
Yeah.
if you look at the line 15, if your length of word is 1, okay, so you just return that itself. So you don't come down here at all, right? So you don't even check if there is a right 0 or not. Correct.
Yeah.
If your length word is 1, then you, even if it is 0, you just return it. But then if it is 0, then all these things start coming up. Okay. So he's checking for if the 0 is on the left side also, extreme left on 17th.
Yeah.
If it is 0, then actually the way he is handling is he's going and looking for the last 0 also. Okay. For the left, you have to still find out if there is a rightmost 0. Okay. If it's not, then only you go and form again the decimals. Yeah, because if it's 0 on both sides, okay, then there will be an extra 0, okay, trailing 0. That is not a valid condition. Therefore, he's checking it.
Yeah.
Yeah, then that's right. But this is more of a string manipulation problem, complete, right?
Yeah, almost like that.
Yeah, it's not a
String.
DP, right?
I just said that little bit of recursion is applied here. That's it.
No, there is no recursion, is it? You are not, see, you are just using two helper functions, and the helper functions are just to break in that strings, correct?
Every combination it is making, kind of. Yeah, it's not a recursion.
No, not recursion. Yeah, yeah.
Like that, I mean, breaking at every point and then.
Yeah, yeah, yeah. That makes sense. Yeah. Yeah,
Yeah.
you made the problem look very easy now, right? So only if you follow those 0 conditions, right? If you have a 0 at the rightmost side, then you have some things to take care of. Okay, and if you have a 0 at the leftmost side, then you have to check if you still have a 0 at the rightmost side, right?
Yeah.
Yeah. Those are the only 3 cases, I think, the corner cases you follow, and then you put decimal at each and every place, and then you form all combinations when you come out from that line 8 and 9, correct, those two helper functions, and then you add that in the result from line 10 to 12. Yeah, that makes sense.
It's like a combination of number of unique binary search trees, right? In left you have this much, right you have this much. You treat every node as a root, and you check from each node that how many trees can be possible. Same fashion.
Okay.
Like for every left, how many right can be found? So number of trees on left into number of trees on right. You multiply them. So those many number of node you got the trees for this if you keep this as a root.
I think so. I slightly remember that. Yeah.
But mainly string manipulation. This is the main crux only. This one.
Yeah. But it's not a very easy problem, correct?
Yeah, this part is very what do you say?
This itself is yeah, it's not a straightforward.
They'll have to take care of
Yeah, because when you start looking at all the rules, the way they are describing the problem solution, they are overwhelming. You think there are many of the rules, right?
Yeah.
So, but when you look at this implementation, it's very clear. It's not much. You just have to look for the left and right zeros. That's all. Correct. So yeah, in this case, he's saying our original representation never had extraneous zeros. So we never start with numbers like these, right? So when you look at all these numbers, what he's showing here, correct? So it makes things more complex, these things, correct? So, but now when you see the way you are implementing, you just have to look for only 0 if it's a trailing 0 or a preceding 0 at the very extreme left and right. And if you handle those cases very carefully, then it's easy. So that is where the problem breaking down comes here, right? In this case, so the 0 placement. Yeah, and then the rest of the part is just you divide the string in varying sizes and then return them back.
Yeah.
Yeah, super. Yeah, I think this is a good one. Because it took a long time for me to even understand, and it was very difficult to come up with a solution very quickly. But I think this makes more sense. Yeah.
Logs I went saw, and then
Mm-hmm.
even in the discussion also 2-3. There are many different types of solutions they have used in discussion.
Mm-hmm.
But I combined 2-3, and then this was much better than.
Yeah, yeah, that's good.
So shall we move to next or?
Yeah. So, if anyone has any questions?
Just a question.
Sorry. Go ahead.
Yeah. Yeah. So, what we will do if the last character is 0?
If last character is 0,
Assume that 33330. So,
that's an
so how we will proceed for that?
So, what is your test case you are trying to say? It is
Okay, assume that there is a last test case example 300. So how we will proceed for that?
okay. Yeah. So in that case, you will come to this, assuming that you are coming in this helper function, right? So in that case, you will come on line. So line 15 is fine. It depends on how you are breaking it, right? 300. So if you are only with one word, you will come out of it. So 30 and 0 will be a combination, but if you have 3 and 0 zeros, right? So for that case, you will come to line 17. Okay, you will see that is true. And then you will come to line 18, you will see that is also true, right?
Line 17 is not true, right? It's 300. Line 17 is check the first first is 0, right? It's not 0. The first number is 3, so it go to line 21.
30 and 0 you look and then check.
So the first test case will be 30 and 0, correct? So this will pass, right? Because this is single 0, this will come out from here, right? So for just for 30 also this will pass, because you look for, this is not 1, okay, and this is also not 1, right? So it will come here. Okay, so this will not come here, right? So 30 is, this is not 0. Oh, sorry. So this is also not 0. Then you are coming here, and then you are coming to the bottom most. If it is not, so then it will just pass whatever the value will be, 30 in this case, correct?
I think
At
that
that.
should be. That's
correct. And then when for, if you go for 300, is 3 and 0 0. So this is an invalid one. So it's not going to pass.
yeah, because last two
Right?
zero.
Yeah. So you can have 30 0. Oh, sorry, go ahead.
Yeah, go ahead. I think some mistake I made. Yeah, go ahead.
Oh, yeah. Did you change something there?
No, it's index. Looks like some index I'm giving wrong.
So in that case, it should be 30 and 0. I think that is only one valid answer. Correct. So I think you cannot break more than that. So because if you break in 300, so you have 0 at the left side as well as the right side. So this is not valid. Okay. So this is the only value you're going to get.
In this case, yeah.
Yeah.
Okay.
Yeah, but it's a good interview problem because of a lot of edge cases are there to maintain.
Yeah. So that doesn't fit in the rules, right? You cannot have two zeros, both at the trailing and the preceding. Yeah. Yeah. Yeah, you'll have to make some modifications there, I think.
Yeah, that look weird because on line 15, check the length of the word is at least 1, right?
Yeah.
Or it's 0. It could be 0, and then they go to line 17.
Yeah, you take care of that later, I think, right? Sure. Yeah, no problem.
Going to.
So next is like network delay time. So we are given n nodes from 1 to n, and you are also given times list of as directed like the u to v. Like u to v is the what to say destination, source and destination, and w is the time taken, time it takes to go for the signal to go from source to target. You have to send the signal to from given node k and return the time it takes for all the n nodes to receive the signal. If you start from 2, right?
Mm-hmm.
Yeah, that look like correct. But yeah. Well, can you scroll up a little? It say if we cannot find the answer, we return -1. So in what case we cannot find the answer?
When they are not connected, that is one thing. Or we don't have any directed graph. It might be like if we take if we take k equals 2 and we don't have any edge from 2 going to 3 and 1, but we have a reverse way. Yeah, what Shashank was saying.
Infinite it becomes.
Yeah, or maybe it's if it's a cycle. Yeah, but if it's a cycle, still it can reach others.
They have only one example. Okay. No, self loop also. No, is it?
No,
Self
it's not loop.
loop.
It's 1 to 2 and 1 is the weight. So 1 is the u in this example 3. The first one is u. The 2 is the second 2 is v, and the last one is w.
Yeah. And it -1 because there's no outgoing edge at node 2.
Yeah. Once it goes, signal will never come back.
We have an edge from 1 to 2, right?
But 2 to 1 we don't have.
2 to 1, there's no.
Yeah, why do we need 2 to? Oh yeah, okay, because you are starting from 2, correct? Makes sense. Yeah.
So from here you have to go, but we don't have. Yeah.
So what about example 1? You have 1. Okay.
Yeah.
So that is correct. Yeah. So this looks to me, because when I looked at this problem, I thought it is a very simple problem. Just use a normal BFS, looked like a shortest path problem. Just keep on. It's not exactly a shortest path, but keep on looking the shortest path to all the nodes with the weights, right? And then maybe do the BFS way. But it didn't work actually. For some of the test cases, it failed.
Well, in this case, we look for the not the shortest one, but the longest one, right? So how would?
Yeah, that's true. But I actually started with, okay, let's do the BFS way, okay, and go through all the levels. And at each and every level, when I'm going for each and every node, I calculate how much the minimum time I'm taking with the weights, right? And then keep a note of it. And then whichever is the least maximum of all the minimums, then return it. But that didn't work. Yeah. So yeah, my bad in that. Yeah, Shashank. So what were you trying to say?
I'm saying Dijkstra, like it looks like relaxing the edge. I mean, shortest possible path we do, right?
Right.
So that is what.
So Dijkstra is the solution here, right? In this case.
Yeah.
So if you think of the BFS, that is the only way we can do specialized BFS way.
So if you are at this node, you just this whatever value as this edge is the edge. I mean this weight, right? So if it is lesser than the other part, then you relax this edge. Otherwise, you remain as it is, right?
Mm-hmm.
So this
Yeah.
is yeah. Go ahead.
Yeah. So for me, I really don't understand what it is, but I just follow the Dijkstra if it is that way, right? Yeah. So you're trying to explain it, right? How to relax it.
Yeah.
That makes sense. But then,
I
okay, the Dijkstra way we go usually pick up the most minimum value and try to find using that node all the neighbors, right? That is what you're trying to say when you're saying you're relaxing the edges, correct?
the minimum it will
Okay.
update.
And now I got it. Yeah. Okay.
But BFS, I'm not sure.
No, it won't work because if the Dijkstra is also again a specialized BFS, right?
Yeah,
Yeah.
it's a BFS.
So priority queue.
Using a priority queue, yeah.
But even with Dijkstra, we
Mhm.
still need to detect if we be able to reach all the node within the network, right?
Correct. Yeah. So at the end, when you do all this, you still have to go and find out if everything is visited, right? Something like that.
Mm.
Otherwise, -1 will return.
Otherwise,
If it
yeah.
a union, no, I saw union, but I don't recall it.
You are saying union find?
Yeah.
How can we do that? I don't think so because you still have to go and find the weights also.
No, if it's a
Correct.
disconnected component, then you can never reach, right?
Yeah, but that actually you can because you still have to calculate the value. In case if you are able to reach, then you have to return the value. But then you will do a union find for finding just the connected components, and then you still have to use another algorithm to find the values also, right?
It will become complex, yeah.
That will be
Because
yeah more complex to do it, yeah, and additional work.
yeah.
So I think Dijkstra works perfect, but the solution or maybe even the what you say, the hints and everything, even the related topics, he talks about DFS.
Oh,
Okay.
in this,
Right. Yeah. If you go down and then if you look for the related topics here, so maybe I didn't try it, but there might be a way to just go DFS way, right, and just find out what is the maximum path, and
yeah.
then for each and every path, the related one, not the hint. Yeah.
Okay, related one.
Yeah. So if you see there, he talks about the DFS also.
BFS also is related.
Mhm.
BFS because of shortest path, right? He was talking.
No, DFS, the depth first search, right?
BFS also he has written.
BFS is, I think, because for the Dijkstra and the heap, they together come with BFS and heap, right? So Dijkstra uses BFS and heap, and the graph
That's
also, yeah. But I didn't understand DFS. Maybe it might work. Try that. There is a possibility there might be someone implementing using DFS.
Let's say 1 to 2, you started your call from 2, but you can't go to 1, right? In the third example, -1.
Uh-huh.
So you were about to start from 2, but you can't go to 1 using the DFS, right? So that itself shouldn't give, that will give -1.
Okay. Uh-huh.
But what about the first case? First, you are starting from 2.
Mm-hmm.
So from 2 to 3 you went, and then you'll backtrack, and then you'll go from 2 to 1.
Mm-hmm.
Again, you'll backtrack, right?
I don't know whether you have to really do a backtracking in that case because see, you go from 2 to 3, that is one thing. So you have covered 3, okay, and
Yeah.
then you update its whatever that value will be. In case if you have another shorter path from the other place, then you can always look for that value and I can update it. But then you still go to 4, okay, from 3, and then you have covered 4 also, right? So the same
Yeah.
thing you go to 1 and again take care of 1, And so when you have all the values of 1, 2, 3, 4, so you will still have to maintain some global vector or an array where you keep on updating these values of the least whatever those signal values are, right? So when you come out of it, then again you go through that vector and or that array and find out if whichever is the maximum value and then return it. Correct. So I think that way the DFS also should be fine, right? Even if the time complexity might be slightly more.
But
Maybe I'm just thinking loud. I don't know.
and this implementation is also not exactly Dicastra. Only a part of it is Dicastra. This part.
Okay.
The relaxed part, because yeah. So I'm just creating a first a dist vector, filling with what you say, distance vector, everything with plus infinity, and the last one, kth minus one, like because from there you are about to start. So that I'm and now going to n minus one, and for every parameter in your times, I'm checking the source plus the time taken to reach the destination. This is the relaxed part. If that is less than your target, then you update your target with this one. This is what Dicastra does, right?
Well, that the whole thing is a complete Dijkstra only, right? So if you are maintaining a distance vector, okay, with infinity, and then you are actually setting on line number 9 for that source, the value will be 0. But only one thing what I don't see is the priority queue part, wherein you actually pick up the least value first to go for its neighbor.
That is what I was thinking. No heap is used here, so how it is? But line 12 and 13 is what you said.
No,
That
so
statement.
right. So what you are trying to do on line 10 is actually going through each and every node again and again, right? So you are actually you're going through all the nodes. Okay. So either you do it that way, because I think there are different ways of doing this implementation. So you are actually having an additional for loop, which you can easily avoid that using a priority queue, right?
Oh, yeah.
So, but here you will do all these things which are on the inside for loop for each and every node. You don't have to do it actually. So you just pick up whichever is the node which has the least value, okay, the current least value, and then actually find or do the relaxation for that node and then move to the next nodes.
Next one. And then max of distance I'm returning if the distance is less than this.
Yeah, but maybe it is working because you actually also almost doing the same thing, right? But then you are starting from any node. I don't know why that might also. Huh.
It should have started from from where they have mentioned, right?
Yeah, because if you have a value where your distance is infinity, and then you are starting from that node, that doesn't make sense for relaxing it, correct?
Yeah, because
So you need to have a least value to start with, right? At least some value. But if you have infinity value,
not the infinity. Yeah, that's true.
I'm not getting that. Yeah, maybe.
Yeah, that's true. I mean, infinity plus what? Anything you do, it will be infinity only, right?
Yeah. Yeah, but then I will always follow the standard Dijkstra way, you know, just because I don't want to land into a situation where someone asks me about this thing in an interview and say, okay, so and this is if this is not a standard template algorithm, right? Yeah. So it is good, it might work, but then, you know, in an interview, you don't have any compiler to check against it, right?
Yeah.
So there you need to explain it well. So then if he says, okay, there is an infinity value in one of your node, and then you are comparing, then you'll be in a very difficult situation. Yeah.
Then compiler might be doing something infinity plus W. I don't know, like.
I don't know, that might be a Python way.
No, but in times we are running, right? So 2 plus 1, 3. I'm okay. No. Corresponding to that, okay. Yeah. We are picking infinity value actually. because test of u minus 1. Yes. No, I'll have to check that.
Yeah. No
Or then
problem.
keep heap way. Yeah, heap way would be the most utilized here.
Okay, then I will actually just share my one, what I've done with the Dijkstra, the normal generic one. So where I am just trying to look at this problem, right? Yeah, I think so. Just give me 1 minute. Yeah. So this is the very huge code, not like yours, a very simple one.
Actually,
But,
that Bellman
oh, that's the way. Okay. Yeah, the Bellman code, right? Okay, then that's a different algorithm. Yeah, that also should work, right? Yeah, my bad. I didn't recognize it. Sorry.
I saw now.
Yeah. Yeah, there is one way of finding. So you actually find the shortest path for each and every node, right?
Node here. Dijkstra is from single source shortest path, and Bellman code is multiple from every node shortest path.
Yeah, but that is the thing, right? Because that I'm not sure whether in that case which will be optimum, because one of them is optimum, because here you know the source, right?
Yeah.
So you don't have to find in the case if there is the source is not required, because you have to return -1 also. So you don't need to find out. Yeah, well, let's weigh what the time complexity will be. Yeah. So this is the adjacency matrix. Okay, I'm creating here. Okay. Then this is the way exactly what you are doing. Okay, I'm setting this one also. Then I'm using a priority queue. Okay. This is normal min heap priority queue. So I'm pushing 0 and I'm using a pair, right? So the first index will be the value. Okay. And then this will be your node number. So that is the way. So your initial value distance will be whatever is 0. And then you do the Dijkstra, just start from, if your queue is not empty, and then you go inside, you just pop out the first value from the queue, the top value from the queue. It's a priority queue min heap. And then you look for all the neighbors and come here for each and every neighbor, do exactly the way relaxation what you are trying to do, correct? So you just find whatever the distance greater than or the distance of the previous one, what you have just popped out, this guy, along with the current weight, what you get here, right? And then if it is greater than this one, then you just substitute the new value to the current one and then push it into the queue. Keep doing that, right? So this ends, and then you look for if all of them are visited or not by finding if there is any value of max in the distance. If it is not, then return -1, or else you find the maximum value and return.
In that case,
Yeah. So this is the Dijkstra, the simple Dijkstra.
standard implementation of it.
Yeah, standard template. Yeah.
So where does it take care of the? You have visit. We have visit set in there, right? And also, where does it take care of, like, if it have loop in there, does it matter? It does not matter, right?
What for? So one is like you have to find out. So visiting you don't need in this type of implementation, because you are using this distance, right?
That is taking care of visitor only. Right.
Sort of, yeah, because you might actually visit more number of times the same one, right? If the values are different, but you don't have to stop them visiting. So therefore, a visited array is not required. But for us, if you want to find if all the nodes have we covered or not, it's like a disjoint one. So you can come here and see if the value is into max. It means none of them, that node is particular node is not visited, right? Because that is what you have initialized to, right here.
Yeah.
So
And
if you,
there is a cycle.
oh, if it is cycle, huh? So if it is a cycle, then how do we take care of it, right?
It will be infinity then, right?
So we still have to find the maximum minimum value in that case. So even if it keeps on more, so you're not going to enter that in your loop in this one at all, correct?
But
So
how
you're
will
not
you
going to push that in your queue. So it's not going to come at all in your priority queue anymore.
Yeah, because there's no negative.
Right. Yeah, if you have a negative cycle, then you cannot use Dijkstra, right?
that's a ban only. I mean, it's not applicable. Dijkstra is not applicable in that case because you'll hit every time you'll relax only. You'll keep on relaxing because negative distance will keep on decreasing every time.
Right. So yeah, so we'll have to clarify this value of W, right? In that case, it should be always positive.
Constraints, I think they might have given positive, right?
Yeah, in that case, it is from 0 to 100. That is right. But we still will have to get it clarified. But now, if you look at its network delay time, so time cannot be negative,
No.
right? So yeah, in that case, it might be. But if the parameter is something different, like a distance or so, then it is always better to get it clarified. Yeah, then in that case, the extra won't work. So those things have to be decided before even we start implementing, right? Yeah.
Then Bellman Ford will come for negative cycle also.
Right. Yeah. Bellman Ford or the Ford Marshall, right? Those.
Johnson's is also there.
Okay. So do you want to discuss about your Bellman Ford, what you say, that algorithm again?
Yeah, sure.
So it's the Bellman Ford, right?
That's a Bellman Ford. I took it from here as well. Let me share it. Yeah, this one I was saying. This is a Bellman Ford. O into E it's taking and your SPF a single point. SPF is what? This is your Dijkstra, which is taking what do you say? E plus V log V, right? And, Floyd Warsaw is working also here. Anyone can answer why the solution for Bellman Ford should loop for n-1?
Yeah, can we actually go in the top section first? Actually, look for. Okay,
Code,
what
right?
we are looking for, Bellman Ford is going for time complexity of V into E.
Yeah.
Okay, and if you go for Dijkstra, how much it is saying?
E plus V log V.
Oh,
This
okay.
is more.
So this is slightly better than that. Yeah, okay. And so we can, so yours is Bellman Ford?
Mine is Bellman Ford, yes, this one.
Okay.
Yeah.
So still that is not bad, like I think Ford Marshall, right?
Ford Warshall, yeah. Yeah, this one.
Ford Marshall, sorry.
So this is VQ. This is worse than those two, right?
But this handles the negative cases.
Yeah.
Right? I think so. Yeah, I'm also not. Okay, but it's time to actually go through this, revise them again. Okay. Yeah. So if you are able to use Dijkstra, better use it because first of all, it's very easy compared to the other, and secondly, the time complexity is slightly better than the Bellman Ford, right? Yeah, because Bellman Ford goes through each and every node, right? And then he starts tries to find all the values using that node.
Given node, yes.
Yeah. So that might be an overkill in our application, but in case somewhere we need it, then yeah, there is no other way. We'll have to use Bellman Ford. In that case, that will be more better because if you use Dijkstra and above that you use another for loop to find each and every node's value, that will be too much then. So then Bellman Ford is more efficient. Yeah.
This is a new algorithm, shortest path, faster algorithm. First time I'm hearing.
Yeah, maybe.
Single source shortest path was there, right? SS.
So shortest path faster algorithm, it might be like a BFS, one advanced version of it. Yeah, I don't know.
Yeah, BFS only looks like from the.
Yeah, then he's using weights also. In that case, if you have weight, then the normal BFS will have to be tweaked in, right? So again, if you look at the relaxation part, whatever he's doing in that, he's using those conditions to fill in your normal Q. But it's like a normal BFS along with the relaxation of your bell and extra. Okay, that might be a good thing. No problem. Yeah, thanks for bringing this up. Yeah, it's good. Yeah, thank you, Shashank. I think we are close to time.